Good morning, class. Welcome to wintertime, at least as we know it for now. Uh, Hopefully everybody's doing well and staying healthy. The change in weather again is nice, but brings new challenges when it comes to health and all. But I hope you're doing well. Like I promised, I think by today I will have up a message for the final. I just wanted to get a few things squared away with scheduling for my classes and come up with a message that would be applicable to everyone. So I hope, like I say, that you're able next week to do some planning. Once you have the message from me, you can coordinate your finals week at San Jac. And that's why I want to continue to give you plenty of flexibility with the window of time. So that will not change. It will be the same as for the previous test, and the formats are the same, and the test work and all will be the same as the fourth test. So no surprises. The one thing about the testing format is that it never changes throughout the term. So that's a good thing. So what I want to do today is to complete our journey of pre-calculus and discussing in a more general way the binomial theorem. And again, when you get to calculus 2, you'll actually extend the binomial theorem to non-integer powers to learn a little bit more about cube roots, square roots, rational functions, and things of that nature. So the binomial theorem is again one of those objects of extreme importance, just like we found out with when you started your training in geometry with the Pythagorean theorem, and then of course Professor Ron's professing that the geometric progression is so important. The binomial theorem holds another substantial place in mathematics. So what I want to do now is share my screen and just get us thinking about some of the ideas that we need to learn in order to use the binomial theorem in a more general setting. So I'll remind you that we have actually used the binomial theorem pretty much every day of this class. Just to remind you before I start talking about factorials and coefficients, let me just write down a couple of examples where we would use the uppercase A and B. When I do the binomial theorem, I'm actually going to use lowercase letters to mimic what Dr. Stewart does in his text. But here's an example of the binomial theorem. Right here, we have a binomial A plus B, and we use this so much, it's like without thinking about it. A squared plus 2AB plus B squared. Now, of course, we can always just say A plus B times A plus B, but we do this so often that we know this formula. And it's really not an issue to multiply A plus B times A plus B. But as we get more and more terms, that is, as the positive integer here gets larger, that begins to be really a lot of work. Not that we mind a lot of work, but if there's a way to make the process more efficient, we would certainly want to be able to do that. And just to remind you, one that I use all the time, let me just write down the A minus the B. Of course, we could have A plus a negative B cubed. Here's one that we've used that we actually talked about the very first week of class. So again, this is a binomial raised to the third power. And this was A cubed minus 3A squared B plus 3AB squared minus B cubed. So that's as far as we went with the binomial. We have the difference of squares, we have the difference of cubes, the sum of cubes, but that's not what these are. Again, sometimes it was easy to get confused if you weren't paying attention, and or we have these mental lapses that we think we see something and translate it into something that it's not. So these are instances of the binomial theorem that we have already used. And so what I want to do is say, okay, well, if that's the case, is it possible to actually generate these with another type of formula where we can actually generate the terms with the coefficients. And if we want to go to 4, 5, or 6, or some other natural number, is there a way to do it without having the task of the distributive law over and over? Again, we often think that hard work gets us where we want to go, and that's certainly true, but we want the hard work to make sense as we work through these items. So first thing I want to do is talk about the factorial function. And let me adjust my computer. You all, it's like my head's cut off. There we go, that's a little bit better. I've been adjusting my computer position several times, and I don't know if it's making it better or worse. Maybe I'm just getting taller. Now, what I want to do is talk about the factorial function. So let n be a natural number. Okay, so n is a natural number. And what we want to do is define, at least in terms of words for now, define n factorial. N factorial to be the product of all positive integers less than or equal to n. So I know you've seen this before if you've done some elementary counting arguments in probability or some type of elementary combinatorial arguments, you've seen the factorial function. So the thing is that we don't often write n factorial. The notation looks like this, and it's kind of odd, but I'll certainly be using it a lot today. The notation for n factorial is n, and what we basically use in English as an exclamation point. So we say n factorial. Now, if we think about what we've described here, if we do 1 factorial, that's just the only positive integers less than or equal to 1, that's just 1. So this by definition would just be 1, okay? And then 2 factorial, we want the product of all positive integers less than or equal to n, or in this case 2. So we can do a descending product and just say this is 2 times 1. And just write them in that order to keep up with them. This gives us 2. And then 3 factorial, same thing, 3 times 2 times 1, the product of all positive integers less than or equal to 3. So that's going to, well, it looks like it's going to be recursive. Well, that's 6, right? And then 4 factorial, 4. And you're thinking we really don't have to put in the 1, but you can, you know, for now, 3 times 2 times 1. So that would be 4 times 6, or 24. Let's do one more. Do as many as you like. So this number grows pretty fast, actually quicker. Actually, it's somewhat asymptotic to the exponential, and so it grows pretty fast. It's an amazing function. And then 5 times 4 times 3 times 2 times 1. So that'll be 5 times 24, which will give us a 100 plus a 20, which is 120, etc. So what we're seeing here is that with the factorial function, we're noticing a recursion, so to speak. That is, note, we can think of this as just a sequence, a sub 1, a sub 2, a sub 3. So we could say that if a sub n is n factorial, we can write this as n times n minus 1 factorial. So basically, we look at 3 factorial and say it's just 3 times 2 factorial. We look at 5 factorial and say that's just 5 times 4 factorial. So this is a recursion. Now, again, the factorial function is really useful when we look at it in terms of ratios where maybe some of the terms absorb and the numbers get a little bit smaller, so to speak. So one thing that we will often find to be useful in dealing with the binomial theorem and factorials is the concept of 0 factorial, because what I've defined up here is just for the natural numbers, and we don't always consider 0 to be a natural number unless maybe you live in Great Britain and they just include it. So just to keep us from dividing by 0, we define the following. We define 0 factorial to be 1. Now this is consistent. This will be consistent with everything that we do. Again, this is our convention. Just like we have conventions in trigonometry and the conic sections, you know, we have to state some rules. So in order to keep all of our mathematics correct, we're going to be very happy to have 0 factorial to be defined as 1. So this factorial setup, again, there's just like other things I've talked about in this class, inverse trig functions, you could spend days and days studying their properties. So why do we care about the factorial function? Well, tied to the binomial theorem is an object called a binomial coefficient. And the binomial coefficient uses factorials in its definition. So here's the next definition, for n, at least now, greater than or equal to 0, and of course, this will be generalized in calculus too, and k, in this case, between 0 and n, where we're going to take n and k to be integers. We define the binomial coefficient. Now, of course, these objects were called the binomial coefficient because they turn up in the binomial theorem. And the history of this object is interesting. Now, like I said before, notice we kind of need this 0 factorial basically because I'm allowing n to be 0 and k will run from 0 to n, and all of these are integer values. So except for the 0, everything's a positive integer. So we're going to define the binomial coefficient, and here's the notation. This was developed in the 19th century. So this is not something that's been, I mean, there's so many ways to write this and so many ways to think about a binomial coefficient, but we're going to focus on the number theoretic ideas. This will be defined as a falling factorial, and my notation is a little bit different from some of the works. I'm using a notation that I learned as an undergraduate at Carolina. It's going to be called the falling factorial. So sometimes it's done with the superscript, but I think that's confusing. So I'm going to say, I'm going to call this n perm k, and I'm going to call the binomial coefficient n choose k, because that's an easy way to refer to it, n choose k. That's thinking about the probability aspects. Basically, looking at subsets of size k unordered from a set of size n, but that's another course. So now, when we look at this, I will define what this is, the falling factorial divided by k factorial. Okay, now what is the falling factorial? Well, what you do is you start with n and you decrease 1 each time like we're doing this, but you stop at the k factor. That is, once you hit k factors, you stop. This is kind of like the stopping point. So if that were a 2, we'd have n times n minus 1. But what does it look like in general? Well, in general, it would be n times n minus 1. And I'll write a couple of these down, but it gets a little bit long-winded. So we're just decreasing by 1, just like we have factorials here. And then, of course, the kth factor will be n minus k plus a 1. And then, of course, the next factor will just be n minus k, because these just differ by 1. So the falling factorial basically is often stated n perm k. I'll sometimes say n perm k. N choose k for the binomial coefficient if we don't have anything better to call it, and n perm k for what we call the falling factorial. And then, of course, we divide by k factorial. Now, there's several ways to there's several identities that we're going to use, or at least a couple, not several, just 2 that are of main importance to us. But because we have this 0 factorial defined to be 1, we're going to have 2 kind of sidebars. That is, anytime we have, using this n choose n, that will be defined to be 1. Because basically, if we follow this deal here, we're going to actually end up with a 0. I mean, not in this case, but in the next case, this makes sense. But then this says that n choose 0. Again, we'll have a 0 factorial here. Notice this will just be n factorial divided by n factorial to give us 1. So that's really okay. We'll just go ahead and say that follows Professor Ron's formula. And then, of course, here to incorporate this, so we don't get into trouble, we'll just go ahead and define this to be 1. So these are like the extreme cases. So if you're thinking of choosing a subset of size n from a set of size n, there's only one way to do it if they're unordered. So n choose n will be 1, and n choose 0 for convenience will be 1 if we choose to define 0 factorial to be 1, okay? So these are just kind of extreme cases to keep us on the straight and narrow and not divide by 0 and get infinity when we don't want it. Now, let's just look at how we can use this new object here. For instance, let's just try a couple of computations. Let's do 5 choose 2. Okay, well, we'll use Professor Ron's definition. So we'll say 5 perm 2. Okay, remember n perm k divided by 2 factorial. Now you can write these all in factorials and rewrite this, but that's of uselessness to us because it's just too much stuff. This is easier to work with. So now we do the 2 factors in the falling factorial. So 2 of them, 5 times 4. That's 2 factors, stop. And then 2 factorial is just 2 times 1. And then, of course, the 2 will absorb into the 4, and that will give us a 5 times a 2, which is 10. So 5 choose 2, or the binomial coefficient 5 choose 2 is 10. Okay, pretty simple. Let's try another one. Then you're thinking, if the number downstairs is kind of large, this is going to be a more difficult calculation because there are more numbers. So we're going to find some shortcuts to make our life a little bit less arduous here. So let's try another one. Let's just say we do, I don't know, 6 choose 3. So this will be 6 perm 3 divided by 3 factorial. Okay, and so now when we look at this, we're like, okay, we need 6 perm 3, so we need the falling factorial. So again, decrease by 1 each time, but then stop after the third factor. So now you can see this is indeed n minus k plus 1. That is, this equals 6 minus 3 plus a 1. That's 7 minus 3, which is 4. So this is exactly what that is right there. Abstract, concrete. Abstract, concrete. And then 3 factorial is 3 times 2 times 1. Now, of course, you can pair these up. We have 6 over 3. And then the 5 is just that nice prime number. And then we have the 4 over 2, just to pair them up when it's easy to do. So this will give us a 2 times a 5 times a 2. So that's a 4 times a 5, which is a 20. So we're thinking, well, not so bad, but can be horrible if we don't think about what we're doing and maybe think about some identities that would be of use to us. So if you haven't seen the binomial coefficient before, you have a nice, simple, well, at least usable definition to compute them. Now, the thing is that with the binomial theorem, there's some identities that we have with the binomial coefficients that will actually make our life easier and also create a triangle of binomial coefficients. So let's look at that. So here are 2 identities that will be useful. So 2 useful identities. When is an identity not useful? Maybe that's redundant, but well, I guess if it's not useful if you never use it, right? That's like saying, oh, here's a useful trig identity. Trig identities are always useful, but I'll tell you that you'll use more, certainly some identities more than others. And those are the ones you'll always keep in your brain. So the first one in this case will be the one that helps us with computation. That is, you're thinking about picking subsets. We can verify these with the definition. That is, n choose k will be equal to n choose n minus k. So if you think about picking subsets, like if you were picking subsets of size 2 from a set of size 5, well, once you pick that subset, you've left 3 behind. So you've automatically picked 2 sizes of subsets. So basically, this is kind of an intuitive deal. That is, n choose k would have to be equal to n choose n minus k. If you think about that in terms of the counting technique, again, that's another course, but I always like to emphasize that because it helps you to remember this. And of course, you're going to look at this and say, these are going to go up and then going to go down. And so we're going to choose the one that has the smaller, lower number. In this case, when we do the coefficient, if k is smaller, we compute this. But if it's a little on the large side, we'll do the subtraction to make it smaller and then say, oh, I'd rather compute this because there'll be less factors in the falling factorial, easier computation. And then 2, this is called the Pascal identity. Blaise Pascal was a French mathematician who promoted the calculus and did work in probability, just a guru of mathematics. And again, lots of these ideas were formulated earlier, but then the nice notation came along later, which of course we enjoy because we're lazy and we like convenient notation. So it's going to look like this. And this one's not very obvious. N plus 1 choose k can be written as a sum of factorial. So this is a recursive definition. This is n choose k minus 1 plus n choose k. This actually is the Pascal triangle. Well, I'll just write into here. I'll just say triangle. This is the identity that we use to form the triangle of binomial coefficients. This is a recursive process. So to get this one with the larger value of n, we can add lower values of n coefficients. So again, this is not very obvious, but let's just look at these and see how they can be of use to us. So for instance, say we had something like this. Say we had 7 choose 6. Okay, so here's an example. And we're thinking, wow, that's 7 perm k, and 7 perm 6, where k is equal to 6, and then 6 factorial. That's a lot of work. But we're thinking, okay, let's just use this identity and say 7 minus 6, which is 1. So by identity 1, this is just 7 choose 6 is just 7 choose 1. Well, how simple is that? So by using this identity to develop a lower number, so to speak, the new k, which is smaller, we have a simpler computation. So this would be 7 perm 1, not very difficult, divided by what? 1 factorial. So that's just 7 over 1, which is 7. So now what we're seeing is that n choose 1 is always n. Well, that's not a proof, but again, we can see that now if the lower number is a 1, then we don't have much work to do. That's 7 perm 1 divided by 1, which is just 7. So we can see that when it's convenient, using this identity makes the computation easier. So we'll just say easier computation. It's like when you break things down with a prime factorization, you can let the numbers do the work with symbolic computation. So symbolically, this is hugely simpler. And so we elect this. Now you can do the other, but why would you ever want to do that? Now, of course, depending on how you write things and depending on the factors and all, it may seem pretty simple that most of the factors would go away. But even if you don't do this, you'll still get the same answer. You just have to work a little bit harder to do it. Let's try one more example similar to this. Say we have something like, let's look at this, 9 choose 7, something like that. So we'd have a 9 perm 7 divided by 7 factorial. Well, we didn't even write down 7 factorial. That's 5,040. So I don't want to do that. So I'm going to say, okay, I'm going to use 9 choose 9 minus 7, which is 2, using this identity. And so this is easy. So this is 9 perm 2 divided by 2 factorial. So this will give us 9 times 8, stop, 2 factors, falling factorial, 2 times 1. So of course the 8 and the 2 absorbs, that gives us a 9 times a 4, and we get a 36. So computations are often made simpler by looking at definitions and seeing what the definitions will provide us in terms of theorems. So we look at this as a theorem, an identity that we can validate, and we look at this one as a theorem. So just to get a little bit of practice before we do this one's a fantastic time saver, which I'll share with you. But let's just kind of look at this and say, why is this true? Let's get a little bit of practice with the definition of the binomial coefficient and use a little bit of algebra. Because I want you to, when you get to calculus, I don't want this to be the first time you've seen this and then you're like, I don't know what's going on with the binomial theorem. So now this will be n perm k divided by k factorial. I'm kind of giving you the notation here so you think falling factorial, k factors. You can often leave this out and go right to the falling factorial product and not write this. So, but we won't always write that. So this will be n times n minus 1, and we'll just dot down to the kth factor, n minus k plus a 1. And here we have what? K factorial. Now, when you look at this and you think about, which one would be easier to to remedy, so to speak, and to make simpler in the sense. So you're thinking if we want to get to here, we kind of need an n minus k factorial, right? So we're thinking, okay, let's just throw caution to the wind and say, you know, we want to get this downstairs, so we need to kind of put it there. So when we take this, let's just do that convenient one and say n minus k factorial, n minus k factorial. So when we look at this, we're thinking, all right, well, that looks good. That looks good. So let's just see what that'll give us. So now notice this is n down to n minus k plus 1. So the next factor here will just be n minus k when we take the 1 away. So this is going to run us on down to 1. That is, notice here, the next factor is n minus k, and then this is falling down to 1. So this part gives us the n factorial. So again, by definition, so this is n factorial. And then when we look at this, well, we've got the k factorial and the n minus k factorial. So we'll just write that in. Now what we want to try to do is absorb the k factorial, because we know we need n minus k factorial downstairs. So let's absorb it. So let's write this as n minus 1. And let's just march on down to k plus 1. So that's the factor right before k, and then write k factorial. And so we have k factorial, n minus k factorial. Now, when we look at this, we're thinking, okay, so we're just getting kind of clever. So we take the n factorial and we march on down to k plus 1. And then the next factor would be k minus 1, k minus 2 on down to 1. So now we see the k factorials absorbed. So this will be n times n minus 1 down to k plus 1. And then we have our n minus k factorial. Okay, now, when we look at this, we're thinking, okay, well, we need this to be n minus k plus 1, but that's exactly what it is. Notice, this is n minus k plus 1. Because notice the n's absorbed and we get minus k, so this is k plus 1. This is exactly that. So that's just our definition. Oh, well, I guess I'll write with the correct order here. So this gives us n times n minus 1. And now we can write this as the n minus k plus 1. So now in our regular definition, the k has been replaced with n minus k, but that's what's downstairs. So n minus k factorial. So again, remember, in our previous definition of n choose k, we have n minus k plus 1 divided by k factorial. Now we replace the k with n minus k, which we've done here. So n minus k, n minus k. So by definition, this is just n choose n minus k. Now, you're thinking, wow, it's probably easier to think of this in terms of choosing the subsets. But these types of calculations are very important when we're dealing with factorials. So we don't want to say, oh, well, you know, that makes sense, and who cares about the definition? But the idea here, this is like doing trigonometry. We have a definition, like we have a unit circle that provides a particular arithmetic. The binomial coefficient provides a particular arithmetic. And so if we wanted to show that these are equivalent, we can just go by the definition, using some convenient algebra to put the right denominator downstairs and then rewrite the n factorial to absorb the k factorial. And then notice that this is simply the last factor of the falling factorial. So again, not abstract at all, not as abstract as induction, even though now induction probably doesn't seem so bad that you had a chance to look at it. So what we're seeing here is that all of these can be actually shown via the definition. So I just wanted to give you an idea of how we work with this. Now, let's look at the Pascal identity. So again, just take this as a means to understand why this works and just utilizing the notation to move the computation forward. So indeed, n choose k does equal n choose n minus k, just like we say 9 choose 7 equals 9 choose 2. 7 choose 6 equals 7 choose 1. The abstract proof right here. So now, what about the Pascal? Well, let me show you something about this particular identity that's actually really nifty. So let me move this over here. So Pascal, and I think normally what I do is I write the binomial theorem, but let me just go ahead and look at Pascal. This will be kind of fun. First, what we're going to do, ladies and gentlemen, is we're going to draw a triangle that has ones along the edges. And then we're going to move over to another triangle and replace all the numbers with the binomial coefficients. So here, we'll start out this way. So when I say ones along the edges, I'm meaning that. Now we're going to keep going, ones along the edges like this. But to get the number here between these two ones, we're going to add these ones. We're actually using Pascal's identity, but you don't know that yet. 1 plus 1 is 2, right? Okay, so now we're going to put another edge here. And to get the number here, we're going to add 1 and 2 to get 3. Oh, let me look familiar. 1, 2, 1, 1, 3, 3, 1. Oh, that's from way back. Oh, 1, 2, 1. And then we got a negative. So we've got a 1, 3, 3, 1, at least accepting the sign. Oh, okay. Interesting. So let's do it again. So 1 plus 3. Well, see, that's why everybody loves the binomial theorem. This is like the easiest thing we've done in a long time. 3 plus 3 is 6, 4, 1. Let's keep going. 1 plus 4, 5. Now, you've probably seen this before, maybe in a general math class, when maybe your teacher got bored one day and said, well, let's look at Pascal's triangle. And then a 1. So 1 plus 5 is 6, 15, 20, 15. You see they rise and then they fall. They rise and then they fall. Now let's try another one. I'll run out of room. 7, 21, 35, 35, 21, 7, 1. So these coefficients are really interesting. So what we're seeing is that when we add, do like this, that's the identity working right here. That's the identity working. To get the number in the next row, we're basically using the Pascal identity, adding these coefficients. And what's interesting about this triangle is that this triangle generates the coefficients of the binomial theorem where n is a positive integer. So that's amazing. So what exactly is this? Well, let's go ahead and write it down. I'm going to write it down right here. The first one is 0, choose 0. So this is like n equals 0. This is the n equal 1. A plus b to the 1 is just a plus b. This is n equal 2. N equal 3. N equals 4. N equal 5. N equals 6. And n equals 7. So these are just powers from the binomial, a plus b to the fifth. They're the coefficients right there. So what are these actual numbers? Well, they're binomial coefficients. 1, choose 0. 1, choose 1. And now you can see 2, choose 0. 2, choose 1. 2, choose 2. Well, 2, choose 1 is 2. Do that in your head. 2, choose 0. 2, choose 2. Those are the extremes. Those are ones. The ones are the extreme cases, which I've already told you about. And then we'll have 3, choose 0. 3, choose 1. 3, choose 2. 3, choose 3. Keep going. 4, choose 0. 4, choose 1. 4, choose 2. 4, choose 3. 4, choose 4. Do another row. Now you see the routine. 5, choose 0. 5, choose 1. 5, choose 2. 5, choose 3. 5, choose 4. 5, choose 5. And we'll do the 6th row. You can put in the 7th if you want. 6, or maybe I'll do it. 6, choose 0. 6, choose 1. 6, choose 2. 6, choose 3. 6, choose 4. 6, choose 5. 6, choose 6. Obviously, we can go on forever. And let me just go ahead and put the last row here. 7, choose 0. 7, choose 1. So for every n, we're getting n plus 1 terms. 7, choose 2. 7, choose 3. 7, choose 4. 7, choose 5. 7, choose 6. And 7, choose 7. So now what you're seeing is this is truly what's going on. N, choose k minus 1 plus, and we can prove this the same way using the definition n choose k equals n plus 1 choose k. So 6 choose 3 plus 6 choose 4 is 7 choose 4. So here n is 6, k is 4. You see, that's Pascal. So the Pascal identity will generate the triangle. And so you put your ones down, which are the extreme cases, and then you can get all the intermediate numbers in the row by just adding the 2 above it. So this is where students are like, well, I've got raised to the 5th power. Let me just go ahead and write down the triangle to generate the coefficients, and I'll stick them in the equation, and then I'll reduce the arithmetic, with the powers, and I'll be done. So what we're seeing here is this is what we call Pascal's triangle. And we're not solving a triangle like we're doing in trigonometry, the law of cosines or the law of sines. We're simply looking at this as a mechanism, okay, for doing something else. So how is this a plus for us? Well, this is a huge plus. This is a huge time saver when you're taking a test. Why do we care about this? Well, let's state the binomial theorem. So this, I guess, no card time, maybe no card, whatever, or leave it in your brain. But for now, maybe a note card will be good because it's a little bit new. So why do we care about the binomial coefficient? Well, because we want the binomial theorem. So let's write it down. So binomial theorem. Of course, you can prove the binomial theorem by induction. We'll probably have some time to talk about that. If I don't get to it today, we'll talk about it as a nice example. So the binomial theorem, we'll use a lowercase a and b in the theorem since Dr. Stewart uses that. Lowercase a and b. At first, we'll think of these as real expressions. They could be complex. And let me get there we go. Well, see, sometimes when I wave over it, it automatically focuses. So I'm cool. That's good. So let a and b be real numbers and n be, in this case, a natural number. Then, and this is where we get to use our sums, A plus B to the nth power. Again, we want to write a formula. So, of course, we could say this is A plus B times A plus B times A plus B n times, n factors. That's really what it is. But what does the theorem tell us? Well, it gives us a sum, a finite sum. K equals 0. So now we need an index variable different from n. So this is like a partial sum. So when n is not a positive integer, say 1/2 square root or something, this becomes an infinite series. And this is basically how your calculator computes square roots. The binomial theorem becomes infinite. When the n is a positive integer, it's just a finite sum. And we know that when we square a plus b or raise a plus b to the third power, it's finite. So we have n, and then of course our binomial coefficient. Of course, in calculus, the n and the k switch because of notation. So I apologize for that. That's just kind of craziness. That's just convention too, but it doesn't matter. If you know what you're doing, the notation change won't matter. So basically, we're going to have a sum from k equals 0 to n. That's going to give us n plus 1 terms in our sum since we're starting at 0. And we're going to have a coefficient of n choose k. You know what that is. That's the binomial coefficient. And then a will be raised to the n minus k, and b will be raised to the k. Of course, those could be switched out. It doesn't matter. This is just basically going to be descending in the power of a and ascending in the power of b. So when you look at this, you know what this means. You set k equal to 0, you get a term. You set k equal to 1, you get a term. You set etc. K equal n, you get a term. So the binomial theorem says that if you want to expand this, you need all of these coefficients multiplying these powers here. And you can get the coefficients from Pascal's triangle, or you can just compute them separately, your choice. So if we expand this, and this is something you do in your homework, what does this look like? Well, this will just be n choose 0. So that'll just be a to the n because k is 0. Then we have n choose 1. So that'll be a to the n minus 1, b to the first. Again, the sum of the powers or exponents or powers will always be n. So n plus 0 is n, and n minus 1 plus 1 is n. Plus n choose 2, a to the n minus 2, b squared. And then, of course, we just keep going until we max out. So this is k equals 0, k equals 1, k equals 2. And then the very last one, k equal n. Of course, that's a 1. And then, of course, we get another 1, n choose n, b to the n. So the idea here is that the binomial coefficients really help us keep track of how many terms we're going to need. So if you use Pascal's triangle, you can say, okay, well, this is n equal 3. I need 4 terms. Okay, I need 4 terms. So the idea here is that you'll have the extreme terms and then the intermediate terms always. And the binomial coefficients will be generated by the triangle. So let's look, again, we're going to think about a proof of this, but before we do the proof, let's just look at a simple example and maybe do several examples and then come back to the induction proof. Notice this already has a k in it, so we would not switch to k just for reasons of sanity. We keep everything with n, because then that means changing to another index, which is not worth the trouble. So sometimes when we do induction arguments, we just stick with the variables we have for simplicity. Again, with Dr. Stewart, we switched to k for the first time around just for simplicity with the WebAssign again, and that's fine. But as you get more esteemed in what you do, you can be more flexible with the letters that you use. So if we think about this as being a so-called expansion theorem, we can always use this, especially or in the special case when n is a positive integer, without having to multiply the n factors by hand with the distributive law. So this theorem does the work for us. So let's look at a simple example. So it says, write x plus 3 y. Again, the a and the b can be anything. You can make up your own problems with this. In expanded form. So again, this is x plus 3 times x plus 3, 4 factors, okay? So what we want to do is use the binomial theorem. So what you can do at this point is just kind of set it up. A will be x, b equals 3y, n equals 4. So that kind of takes care of the administrative work. And then you're thinking, well, okay, I've got Pascal's triangle. So let me go ahead and I'll write down the coefficients, but I want to generate them so I don't have to compute each of them by hand. And 2 of them are easy because we know they're both 1s. So let's just go ahead and say, okay, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and then the 4th one will be it. So 1, 4, 6, 4, 1. So this is the n equal 4 row, okay? So now we're thinking, all right, good. There are coefficients, at least accepting any signs and any numbers that creep into the calculation. So by the binomial theorem, so use binomial theorem. And this will be x plus 3y to the 4. So we'll write it out. 4, just go ahead. You can write out the sum or just go ahead and expand it. 4, 2, 0, x to the 4th. Just follow this. Plus 4, choose 1, x to the 3rd, 3y to the 1st, plus 4, choose 2, x squared, 3y squared, plus 4, choose 3, x, 3y cubed, plus 4, choose 4, 3y to the 4th. And that's a 4 there. That's kind of hard to see. Let me rewrite that so you can see it. There we go. So this, again, doesn't take a lot of time. Sometimes students will just say, well, I'll forget these, just go ahead and use the triangle directly. But maybe it's good to write them out so you get used to seeing them. And if you need to do other calculations that just include binomial coefficients, you can use the binomial theorem as a backdoor to doing a calculation that would otherwise seem very difficult. So now we'll just fill everything in. So we've got 1, 4, 6, 4, 1. So we have 1 times x to the 4th plus 4 x times 3y plus, just follow it, 6 times x squared times 9y squared, just squaring the 3y, plus 4, I'll just put the dots in, times x times, okay, 3 squared, 27y cubed, plus 1 times, well, now that'll be an 81y to the 4th. So those are powers that we know. And so when we reduce this, x to the 4th plus 12xy plus, and these are easy numbers, thank goodness for that, 54 x squared y squared plus, now 4, that's going to give us what, an 8, and a 8 plus a 2, that'll be a 10, 108 x y cubed plus 81 y to the 4. So when you look at this, you're thinking, okay, that's better than multiplying this out 4 times and collecting terms. That would be difficult, or that would be harder to do without error. I mean, for instance, you notice sometimes when you're working with trig identities, you've got to knock it out. You got to multiply and collect your terms and use the reduction formulas and things like that. That's fine. I mean, the binomial theorem at least can help you expand, and then of course you can multiply by the distributive law. So in some cases you get the binomial theorem times the binomial theorem, but at least you set it up in a way that you have confidence that once you collect terms you're fine. So now you can look at this and see how we could just generate more and more formulas with the a plus b using the Pascal's triangle. So with Pascal's triangle, you can generate a formula for every road and do it that way if you like. So this is a formal rendering of this, and then we use Pascal's triangle to fill in. But I guess the thing is that you might get tired of writing down all those long strings of numbers. Maybe it's better just to have the Pascal and just fill it in. So again, the binomial theorem is, at least even for n a positive integer, is a big time saver. So let's look at one more example, and then we'll look at the theorem proof. And there are lots of fun examples in this section. You'll like this. It's nice to end with induction and the binomial theorem. These are fun results. They're interesting results, and hopefully will inspire you to maybe study more mathematics, maybe computer science or something where you do more discrete topics. So here's an example. Here they say compute the first 4 terms, and we say first 4 terms, we're going to start with k equals 0 and run up to 3. Remember, k starts with 0 with the binomial theorem, the way we're writing it. The first 4 terms of x to the 1/2 plus 1 raised to the 20th. Okay, so maybe you're doing a computation in physics and you don't need the entire expression, and you're thinking, man, how am I going to do this without the binomial theorem? I got to multiply all this out. What if I make 5 million mistakes? And you probably will. So this is where the famous formulas, like doing sums, they say, WebAssign says use a graphing calculator. Well, you know not to do that, because if that's what you're doing, you've learned absolutely nothing. You learn the techniques I teach you. You break up the sum and use the famous formulas. Anybody can punch buttons into a calculator or punch numbers into a calculator. That's the most useless exercise in the world. The idea is that we use the calculator to get nice approximations. The calculator is a bonus, okay? It's a slide rule that's electronic, okay? So what we want to do with this problem is say, well, I don't care to write down all the terms. Maybe the problem only needs the first 4. So I'll use the binomial theorem to write them down. So we'll just say first term. Now, if you like, go ahead and tabulate over here. A is x to the 1/2. Oh, how fortunate. B is 1. Well, powers of 1 are 1. So how fortunate we are there. So we have b equal 1. That's a good thing. And n equals 20. Not that we even really care about n equals 20. So first term will be k equals 0. So we'll say, well, we do need the 20, so don't let me downplay the 20. So we have 20, choose 0. And then we have x to the 1/2 raised to the 20th power. Okay, well, 20 choose 0, that's extreme. That's just 1. So we get 1 times x, well, 20 times 1/2. Well, this is really difficult. This is just x to the 10th. Power of the binomial. Second term. This is a big improvement. Of course, WebAssign is a useful tool for learning this. So now for k equal 1, remember we always start with 0. The second term will be 20 choose 1, x to the 1/2 raised to the 19th. That is, we decrease by 1. But of course, the other term is just powers of 1, so you can leave it out. You don't need it. It just has no impact. I mean, we like to multiply things by 1, especially when they're convenient ones, but here, this isn't getting us anywhere, so we leave it out. So 20 choose 1, that's an easy one. That's just 20. We just get x to the 19 over 2 by the laws of exponents. Third term. So now what we're doing is we're just picking and choosing. So for instance, sometimes they might say, well, find this term, and you'll use the k, the index value, or they'll say, find the term with this power in it. And you'll just go to the binomial theorem and figure out the actual value of k. It's just that simple. The binomial theorem gives you all of the ingredients that you need to solve these problems. So we've got what? K equal 2. So this will be 20 choose 2, x to the 1/2. Again, we're going to have 20 minus 2, which is 18. Now, of course, we'll use the definition. We'll do the falling factorial, 20 times 19, 2 times 1. And of course, this would just be 2 into 18, which is 9. So of course, the 2 will absorb into the 20 to give us 10 times 19, x to the 9th, and of course, 190. And then the fourth term, now you get the gist here. You see the power of the theorem. So what do we do in math? We keep doing the same thing over and over, but we learn new structures to make the process easier. And then we develop a deeper understanding. So we have 20 choose 3, k is equal to 3, and then we have x to the 1/2 raised to the 20 minus 3, which is 17. So again, remember the b is 1, so we don't have to worry about that. So that makes this problem a lot easier. And then the standard Newton binomial theorem is written with a 1 in it. So that's, the thing is, Newton was a very smart man, a super genius, and his work on the binomial theorem is irreplaceable. We will forever study the work of Newton, just like Ramanujan and Gauss and Euler and all the other geniuses that have preceded us. So 20 times 19 times 18. Remember the falling factorial, 3 factors, 20 times 19 times 18. You don't want to do 20 rows of Pascal's triangle. Not good. That takes too long. When it gets too big, you just do this, okay? Don't do that. That would be a waste of time. So 3 times 2 times 1. So x to the what? 17 over 2. So now what we can do is pair these up because we're lazy. So we'll get 20 over 2, and then we'll have a 19, and then 18 over 3. X to the 17 over 2. So again, we've got a 10 times a 19 times a 6. So this will be 19 times 60. Well, here, let me go ahead and let me not just forget our power of x like it's unimportant. X to the 17 over 2. So x to the 17 over 2. And then, of course, we have a 0. So 6 times the 9, that'll be a 4 with the 5, 1, 1. So 1140 x 17 over 2. So now you can see that we really did need something other than the old-fashioned way. So when you think about how the binomial coefficients interchange, or for instance, help us here, we can think in terms of the Pascal's triangle, or we can think in terms of counting. So if you wanted to prove the binomial theorem in terms of counting, you could as a combinatorial proof, or you could actually prove it using induction. So there are several examples here with the binomial that we'll do. They're kind of repetitive. So what I want to do is take an opportunity to look at why the binomial theorem is true as another example of induction. So we'll just kind of knock this out because I promised I would do it. So now we can say, for instance, note, let's just write this theorem down. This is our P of n. And we get to use some really simple ideas. We get to use the Pascal identity and use some simple ideas about sums to make this very doable. So we're going to say that A plus B to the n is just what we said it was. K equals 0 to n choose K, A to the n minus K, B to the K. So that's our logical statement about natural numbers. And so when we look at that, we're thinking, okay, well, we need to try n equal 1. Does it work? I mean, we know this works, so we certainly think Professor Ron has told us something that is true. And then we say, okay, well, if this is actually true, we'll just say for n instead of, since we've got the K here, I don't want to switch that out and call it a J, and then just that's a notational nightmare. So we'll just say, well, this is true. Let's see that it gives us n plus 1. So instead of doing the K this time, to keep things a little simpler, since we already have a K embedded in the formula, let's just assume n and then bump it up to n plus 1. So that's what I was talking about last time. We stuck with K first, but now we can be a little bit more flexible because you're more erudite now about this method. So first we'll say, number 1, n equals 1. So let's just see, A plus B to the first power. Well, that doesn't take too much work. A plus B to the first power is just A plus B. Okay, does this equal our formula when we replace n with 1? Let's check it out. So 1 choose K, A to the 1 minus K, B to the K. So of course we're going to have two terms, K equals 0 and K equals 1. So with the 0, we get what? 1 choose 0, the extreme terms, not very interesting. And then A to the 1 minus 0, so just get A to the 1. Of course, B to the 0 is just 1, so we can leave that out. Plus K equals 1. Now we've got 1, so we have 1 choose 1. 1 minus 1, that's just A to the 0, so that's 1, and we get B to the 1. So now 1 choose 0 and 1 choose 1 are both 1. Those are the extreme cases, so we get A plus B. So that's a check. So indeed, if we just did it the standard way, we get it also the way by using the formula about the natural numbers. So equivalently, P of 1 is true. So that's what we had to show. So there's now two. So suppose, we won't write this again. We'll just say, suppose P of n true. That is, you don't always have to write this down again. Of course, we would write it down before because we were changing to K, but now if we're not changing to K, so I'm not going to write it down again. There's our P of n right there. So for some abstract n, this is true. So we want to consider bumping it up 1. So consider the following. That is, we know if we raise a plus b to the n power, the induction hypothesis says this. So this, remember, this is the induction hypothesis, which we must use. Induction hypothesis. True or false? If you don't use the induction hypothesis, you have proven the result by induction. Well, clearly false. Maybe you proved it, but you did it differently. And that's okay too. But if the question says use induction, we need to use it. So now we have what? A plus b to the n plus 1. So can we use this to show that this is actually this formula where n has been replaced with n plus 1? Well, let's try it. So this is what? A plus b to the first power times a plus b to the nth power using the laws of exponents. There's my induction hypothesis there, and I can always multiply by a plus b by the distributive law. So let's do it. So this is going to be a plus b times, so we use induction hypothesis. This is actually easier than some of the problems we've done prior to this because it's just so straightforward. The only thing we're going to have to do is pull off some terms and re-index and use Pascal's identity. So we won't be using anything you haven't already been working with. So we've got what? K equals 0 to n, and then n choose k. N choose k, and then we have a to the n minus k times b to the k. Now, to make this move forward in a way that's going to be helpful, we're just going to go ahead and multiply this series by a and then by b, just bump this up 1 and bump that up 1, and then unravel it a little bit. So we'll have two sums, k equals 0 to n choose k, a to the n plus 1 minus k. So we're going to multiply by a, so we're going to have an additional copy of a. So by the laws of exponents, we add 1, n plus 1 minus k. And then, of course, that gives us b to the k. Then plus, now let's multiply by b. K equals 0 to the n, or up to n, and then n choose k, a to the n minus k, and now we've got an additional copy of b, so that's k plus 1. Now, this is where we have to use a little bit of uncommon sense. I always say common sense is not common, it's uncommon. So let's use some uncommon sense and say, okay, well, notice here with the 0 term, we get a to the n plus 1. That's the extreme term for the n plus 1 case. And when k equals n, we get the extreme term b to the n plus 1. So let's pull those away so we can re-index. So this will equal, now we have a to the n plus 1. So that's the k equals 0 term, plus, of course, we get rid of that. So now we have k equals 1 to n choose k, a to the n plus 1 minus k, b to the k. Now we have plus, we're going to remove the k plus 1 term, so that's the n term, or the k n plus 1, so that'll be k equal n. So we'll just ascend to what? N minus 1. So we're going to have to re-index to be able to add these. So this is a way to do it that's maybe not so difficult. And then plus, so this is the k equal n term, and that would be b to the n plus 1. So notice we didn't do anything to these sums except pull off the k equals 0 term here. So now we start at 1, and then extract the k equal n term. So now we end at n minus 1. So we didn't do any major computation here, just pulling off terms, so to speak. And now what we want to do is set this up so we can add them. So here, what we want to do is replace, that is, we want K to be replaced with K minus 1. So K morphs into K minus 1. So if we make this smaller, we have to make this bigger by 1. So this is the change of variable, so we can add these two series. So that's the uncommon sense. And we've done this before, especially with the geometric. So now we get A to the n plus 1. And now we have plus the sum. I'll go ahead and do this in 2 steps, be a little bit easier to see. N choose K, A to the n plus 1 minus K, B to the K. Now we're going to do the transformation here so we can add these two series. So we're going to replace K with K minus 1. So now we have to start at 1 because we made this smaller. We have to make this bigger, and we're going to end with what? N. So we bump it up by 1 index. And then, of course, replace K with K minus 1. And if we replace K with K minus 1 here, we get minus a negative 1. So this is A to the n plus 1 minus K. And then, of course, if we replace K with K minus 1, the 1's absorb, and we just get K. So this is what we did with the geometric. So I wanted to go back to this computation. So again, now we're thinking, oh, but these don't telescope, Professor Ron. With the geometric, we basically got the series minus the series, and that's why the partial sum formula was so simple for geometric. All the terms went away, they absorbed. But now we can add these. Notice we have K equal 1 to n, and these are the same terms. And then, of course, this is just Pascal's identity right here. So the idea is that we set this up so we can use ideas that we already know to move the problem forward. I know that's probably my favorite phrase, move the problem forward. Because when we get at an impasse, we can't move forward. So we have to use ideas we know. So now, plus, let's just combine both of these series. So we'll have K equals 1 to n. And now we'll just put this in brackets, and I'll write this term first. And that's how I wrote the identity. K minus 1, n choose K minus 1, plus n choose K. And then we have the common AB term. A n plus 1 minus K, and then B to the K, plus B to the n plus 1. Now, this is Pascal. That's why I did the work with the Pascal's triangle. This is just n plus 1 choose K by Pascal. So now we get A to the n plus 1 plus K equals 1 to n plus 1 choose K, A to the n plus 1 minus K, B to the K, plus B to the n plus 1. Now, of course, we're done. This is just the K equals 0 term, which we already knew, and this is the K equal n plus 1 term. So now we can just throw it in, and we're done. So this will give us K equal 0 to n, and then we have n plus 1 choose K, A. Of course, now we need the we need the 1 here, and we have A to the n plus 1 minus K, B to the K. So these two terms now, that becomes the 0 term, and this becomes the n plus 1 term. And so now notice, this is our formula when we compare where n has been replaced with n plus 1. N plus 1, n plus 1, from here, n plus 1, and then n plus 1, n plus 1, n plus 1. So P of n plus 1 is true. So this is why I decided to stick with the n as opposed to switching to k, because we already had a k embedded in the formula. And then I wanted all of the identities to look like the way I had stated them to you. And that was the key. But again, that's your choice. We could have switched to k and changed to j as an index, but I thought that was not worth the trouble. So now by induction, P of n is true for all n in the natural numbers. So the idea is this is called symbolic computation, but you already knew that. We've been doing this all term. Everything we do is symbolic computation. The binomial theorem is symbolic computation. I mean, when we think about what we're doing, it's just a matter of manipulating the symbols in a way that gets us to the finish line, so to speak. So now what we're seeing is that, okay, it's not some kind of fluke that this actually works. That is, when we try to compute these terms here, we know that this is correct. We're not just using some fly-by-night theorem that may or may not be correct. So now we see via induction that this is a bona fide result. And what's nice about this is that we have full confidence in this. We simply use this as a way to verify that the particular result is true for any natural number. It's true for 5. It's true for 5 million. Okay. So, and that's where our computer technology is great. So if we needed a computer to generate 5 million terms, it might take a while or maybe more than a half a second, but it could do it. So that's where our technology will take us to the next level, but we cannot subvert the academic process of doing the mathematics. The technology does not take the place of that. It will never do that. And as a STEM professional, hopefully by now you understand that. To achieve excellence, your mind must work like a computer. You must be able to do the deductive reasoning skills to move yourself to the next level. Okay, so let's now that we wow, this works, let's do some more examples. So what WebAssign does is that, of course, they try to make your life difficult in the sense that they throw some things in that are like, how do I do this? I know I'm using the binomial theorem, but try this one. I thought this was an interesting example. It says factor, that is, factor the following. So when we factor, what we want to do is write things as a product, right? We want to write things as a product. When you factor a trinomial, you use Professor Ron's lemma and keep your fingers crossed that you can get AC to be written as factors whose sum is the coefficient of the linear term. Now, that's not always easy to do. Even when you know it should work, it's not always simple. So let's look at this. So we have x minus 9 to the 5th power plus 5 times x minus 9 to the 4th power plus 10 times x minus 9 to the 3rd power plus 10 times x minus 9. This is just smoke and mirrors. This is a nice problem. And then 5 times x minus 9 plus a 1. Now, when you look at this and you think, okay, well, all right, this looks pretty interesting. And now you think, okay, we've got 5s here. This looks like the binomial theorem. So let's just go ahead and write down a few things. 1, 2, 1, 1, 3, 3, 1. So in the small cases, the Pascal's triangle is fine. It gets too large, you get 7 or more, you like too much. And then 5, so we get, here we go, 5, 10, 10, 5, 1. Okay, we pretty much see that that's n equal 5. This is binomial, at least as terms of the coefficients. And so now, when we look at this, these are the extreme terms, okay? These are the extreme terms. So binomial theorem. So it's kind of like that other problem we did. We'll say that we know that this will be 5, choose 0, a to the 5th. That's what this is. And then this term is 5, choose 5, b to the 5th. That equals 1. So what does this say? If and only if a to the 5th equals x minus 9 to the 5th, if and only if b to the 5th equals 1, since these are both 1. Now, of course, we're not looking for roots of unity, but if we take 5th roots, this gives us an a equals x minus 9, and this gives us a b equals to 1. We don't have the even nth root, so we don't get the plus or minus. So by comparing this to the binomial theorem, we have a candidate for a and b. So I'll just call this, and when we look at this, I'll just call this some, I don't know, let's say, let's give it a name. We'll just call it, because it's got 6 terms, 1, 2, 3, 4, 5, 6. We'll just call it S of 6. So I don't have to write it down again. So this implies, by the binomial theorem, S of 6 equals what? A plus b, which is x minus 9, plus 1 to the 5th power. But of course, we can reduce, and that'll just be what? A negative 9 plus an 8, so x minus 8 to the 5th. So this would be a factorization of this using the binomial theorem. So the idea here is that sometimes we can take a result and work it backwards, kind of like doing identities, factoring identities. Sometimes we take the difference of squares from the factored form to the non-factored form and vice versa. So here we've taken the binomial expansion and we've gone backwards to the factored form, even though we might think, well, this is fine for solving equations. This would be horrendous for solving equations. So if you came up with this and you looked at it, it's like, you know, this looks all kinds of complicated, but I think this is the binomial theorem. And if you needed to solve this, this would be very useful. Now, of course, when you get into complex analysis and imaginary roots, this is an interesting problem. But what we look at this in this particular case, we see that we have a repeated root of multiplicity 5. Okay, so the binomial theorem can be very useful worked in reverse, kind of like we use the rational zeros theorem to generate a list of possible rational zeros. That theorem we use in reverse to find rational zeros. So now we're using the binomial theorem in reverse. So I thought that was an interesting example that you wouldn't think about now, but now that you know the binomial theorem and you start noticing these coefficients, you're thinking, I can make some assignments here and be done with this. So that's interesting. Now, there are a couple of examples here that have to do with binomial coefficients where all you have are binomial coefficients. So let's look at it. So look at this example. Say we have 9 choose 2 times 9 choose 7. So that's a problem. So you have WebAssign and WebAssign says compute that. Okay, well first, when you look at this, you're thinking, well, I've got, Professor Ron, you gave us the definition of the binomial coefficient, and I can do that. And so I can compute this and compute that, and I'll be done with it. Okay, but then you're thinking, okay, well, if I wrote out the definition, I should get several terms to absorb. But then you're thinking, okay, why not go ahead and use the identity I've given you? because these are actually equal. Remember, this is 9 choose 2, but 9 choose 2 is actually equal to 9 choose 9 minus 2, which is 9 choose 7. So these are equal, but that's a mess to compute. I don't want to write out all those falling factorials. So now we just observe that by the first identity, 9 choose 2 equals 9 choose 7. When you say 9 choose 2, that just gives you a way to articulate this. You know, in math, when you don't have a phrase for something, it's just really difficult. You're saying, okay, do this. So for like we have sine of x quantity squared, we don't say that. We just say sine squared because, again, we're lazy and we need efficiency. So if we observe this is true, this would just be 9 choose 2 quantity squared. So if I compute this, I'm really computing 9 choose 2 and squaring the result, which, that's fine. So let's do it. Now, if you didn't notice this, it wouldn't matter. It's still, the computation would still be valid. And if you're trying to get finished, you just go with what you see initially and work with it. There's nothing wrong with that. This is just a way to do it. So now, falling factorial, 9 perm 2, 2 factorial. You have to admit that Professor Ron's introduction of this is superior, only because I've had a lot of training. I don't give you things that are abstract to confuse. I give you mathematics that will help you understand if you bother to put in any time. So this is the reason for this. Moving forward, again, I keep saying this, means that you have to look at the mathematics in a way that helps you understand at a deeper level. So like I say, take this and work with this and feel good about it and move to the next level. So now we have 9 times 8, 2 factors, stop, and then 2 times 1. Well, that's easy. So the 2 absorbs into the 8, so that gives us a 9 times a 4. So this is just 36 squared. Well, now, of course, we can be lazy and use the, the binomial theorem? How funny. So this is 30. So I'm going to use the binomial theorem like I've been doing all semester. You know I've been doing this all term. This is the binomial theorem. Okay, so we're going to say 30 squared, which is 900. And then we're going to say 6 times 30 times 2. So that's 180 times 2. So remember, this is the a squared, 2ab plus b squared. And then, of course, 6 squared is 36. So now, again, binomial theorem. So this equals this. Let me just say that. And so this will be 900 plus what? 336, 360. Plus 36. So this gives us what? A 0, a 6, and a 3 and a 9, which is a 12, plus a 36. So 12, and then what? A 6 and a 9. So 1296. So again, you know, the idea here is not necessarily doing it a particular way, but trying a way that you know how to do. So if you're running out of time and you just say, well, I'll write both of these out, notice writing that out is going to take a lot more time and is more prone to error. So this is a good way to practice using the identities. Now, here's another example. Again, if you get bored with this, look in a combinatorics book or go to Wikipedia and look at the binomial coefficient page, like the inverse trig page. I contribute to Wikipedia because Wikipedia is a wonderful resource and it gets a bad rap, but I'm here to say there are some great information on Wikipedia and the mathematics pages are excellent. So if somebody starts dogging Wikipedia, I wouldn't do it. They always send me messages, please, Professor Ron, help save Wikipedia. You know, if I can contribute to something that helps disseminate good mathematical knowledge, I'm going to do it. It's like giving to the SJC Foundation to help our students. you know, sometimes, ladies and gentlemen, as future STEM professionals, you're going to be the backbone of our community, and you're going to have to support things because who else will? So you're going to be the leaders of the future. So I need to help train you with being benevolent, being like the Will Gates of San Jacinto College. Uh, Gates has done great things for COVID, and it's amazing that he's taken his brilliance and his billions of dollars to help us in our time of need. So that's what some of you all will do. Maybe all of you will do it. Rise to greatness. So let's look at this. 5 choose 0 minus 5 choose 1 plus, here we go again. This looks like the last problem. 5 choose 2 minus 5 choose 3 plus 5 choose 4 minus 5 choose 5. And you look at this and say, okay, well, that kind of looks like this problem, Professor Ron. Where is it? You did this one? Oh, yeah, right here, where you started comparing things. Okay, so notice there's not much here. Oh, my papers are running all over the place. Sorry. So when I look at this, I'm thinking, okay, well, this is binomial. Again, n is equal to 5. And so I'm thinking, okay, well, I don't have any problem with this. I don't even have to write down the triangle. These are the coefficients right there, accepting the signs. So then I can say, well, a to the 5th is just 5 choose 0. That's all that's left. And b to the 5th is the negative of 5 choose 5. Okay, so of course WebAssign's, you know, keeping you in the straight and narrow so you don't get the plus and minuses to make the problem work out for you. So here, a to the 5th equals, that's an extreme case. So a is the 1/5 power of 1, which is 1. Again, we're not doing the roots of unity. There are actually 4 other complex roots of unity here, but we're not going to talk about that. That's another class. We're just doing real analysis here. So b to the 5th equals -1. So we'll take the real solution. The 1/5 power of -1 is just -1. So by comparing, just like we did before, the first term, which is the extreme term of the binomial theorem, first and last. So now we have an A and a B. So we'll call this, what is it, 6? We'll call this S6 again. It's got 6 terms in it. So if and only if S6 equals what? We have A plus B to the 5th power binomial. So n is equal to 5. And remember, this means 6 terms. So this will give us, let's fill it in. So we have A, let's go ahead and fill in A, Professor Ron. Let's call it a 1, very good, plus a -1 to the 5th. So that's a 0 to the 5th, which is 0. Okay. Oh, I see, Professor Ron. It's not really telescoping, is it? It's 0, but these are not equals and opposites. Now you're thinking, well, okay, I'll go to the row and I'll fill in the binomial coefficients and just pair them up, because we know we can rearrange the terms and we'll see that they absorb, but it's not going to be the absorbing in the sense that we had before, where they'd be adjacent, so to speak. So if you didn't notice this, you could just kind of fill in the row and say, oh, well, that absorbs that, that absorbs that. Okay, for instance, if you look at this, these absorb, right? These absorb and these absorb. So you could say, well, you know, Professor Ron, that I see what you did here. Here's another way of looking at it. We can say this. We know 5 choose 0 equals 5 choose 5. We know 5 choose 1 equals 5 choose 4. We know 5 choose 2. Well, this is harder actually, equals 5 choose 3. These are all equal by the first identity, but now they have equal and opposite signs. So this would imply that S6 is also 0. So you can choose to do this many different ways, or you can just take the Pascal's triangle. In this case, let's see, where did I do this? Go back to here, okay? Say for instance, we thought, okay, well, I got to get done with this, Professor Ron. So here's this right here. So you could fill that in. And you could say, okay, well, this will be 1 minus 5 plus 10 minus 10 plus 5 minus 1. And then, okay, pair them up and get 0. You could do it that way. I mean, the idea is there's several ways you can do this problem. You can work backwards to the binomial theorem, or you can just say, well, these are equal and opposite. I mean, these are equal, and so we've got opposite signs. Or you could just say, well, I've got Pascal's triangle on my note card. Let me just fill these in. Oh, they absorb each other. So you can do these problems many different ways. And of course, these are the development of formulas for binomial coefficients that are akin to identities. So again, even though the binomial theorem is not an identity, it is a formula, which is extremely useful, like the Pythagorean theorem. It is not an identity, but it is a very, very useful formula. So when you do these, I'm not saying you have to work these all one way. You can choose any number of methods. And these are wonderful for developing the understanding of the actual binomial coefficients. Now, here's an example I want to do. Factoring is very important, but there's an example here that I want to share with you, finding an actual term. So I think you get the idea of factoring. I think I've beaten that up enough. So let's try this. Yeah, here we go. Here's an example. So we want the 28th term, of this expansion, a plus b to the 29th, okay? Now, like I said before, when you look at this and you look at this particular expansion here, you think about what's going on here. This is n equal 29. N equals 29. So this implies n plus 1 equals 30 terms. All right? So we start with k equals 0. So this implies the 28th term corresponds to k equal 28 minus 1, or 27, because our sum starts with 0 using the convention. Okay, so you don't have to memorize this. Just know here that this a plus b to the 29th will be the sum k equals 0 to 29, i.e. 30 terms of 29 choose k, a to the 29 minus k, b to the k. Okay, so this is more abstract. They're not just saying, okay, compute the term that has these powers in it. They're just saying, give us the 28th term. So that means you have to appeal to the convention. We're starting with k equals 0. So this means that we need the k equal 27 term. So this implies, or equivalently, so we go over here and just pull off the 27th terms. That's k equal 27. So we have 29 choose 27, a to the 29 minus 27, b to the 27th. Now the powers part is simple. That's the easy part. But now, of course, we're not going to compute that. We're going to use the identity. This will just be 29 choose 2, right? So 29 minus 27 is 2. So that's the computation for us. And then, of course, we get a squared and b to the 27th. So here's the actual term right here, ladies and gentlemen. So now, if you like, let's just do our calculation. We do the following factorial: 29 times 28, 2 times 1. Again, using the following factorial here in your definition makes these computations easy. And you don't, just we got one to do, we can do it. So we get now, this will absorb into here. So we get what? Now I'm just going to write, I'm going to be lazy. I'm going to write 29 as 30 minus 1. So 30 minus 1 times a 14. And then that gives us a squared b to the 27th. So now what does this give us? Well, we've got, well, let's just add it up. So we're going to get, in this case, a 300 plus, and then a 4, that's a 120. And then minus a what? A 14. A squared b to the 27th. So this gives us 420 minus 14, good old symbolic computation, a squared b to the 27th. And of course, 14 from the 20 will give us a 6. So 406, a squared b to the 27th. So now we're seeing, this is kind of like doing the conic sections where they say, okay, the foci are this and the vertices are this. What's the equation of the ellipse? Because that will give you what? That gives you the A, it gives you the C, and then you know what? C squared equals what? A squared minus B squared. And then boom, you got it. And you got your B squared, you're good to go. So this is kind of similar to that. This is like, okay, we're going to do a backwards type problem. We're going to say, well, we don't want you to compute the whole thing. That's 30 terms. I don't want that. That's crazy. So we use the convention to work into the theorem to extract the correct term. Now, another type of example would be similar to this, and you can work on this for homework. So do the same for the following example in your web assignment. So here's another thing, and work on this. And if you have some questions about this, you can come to my office hours today. So here's a homework example. So compute, this is what I was talking about before. Compute the term containing, excuse me, containing b to the 12th of this particular term, a plus b squared to the 14th. So what you want to do here is figure out what the binomial theorem says about this, and then determine the k, which will give you the power of 12, and that'll be easy to do. So write down the theorem for this, determine the value of k, and then you're back to this problem. So you get the value of k directly. Here you had to kind of work for it. You're given the 28th term, which is actually, in this case, k equal 27, because our theorem index starts at 0. So try this one here, and I guess if you have questions for that, please come to my office hours. So like I say, I'll get up a message about the final exam. There is a practice exam on Blackboard that just kind of goes through the basics. Remember, the final exam will be comprehensive in the sense that we'll cover everything. There will be some new material, of course, with the sequences, the geometric, and the material that we're covering with this, but it won't be an overabundance. Of course, there will be coverage of it, but it will be nice and spread out. It's not like you're going to get 80% new material. Unfortunately, that would be a much easier test. So there will be coverage of the new material, but pretty much make everything an even distribution. That's just the way you're used to this at San Jack. That's how we do our final exams. And so next week we will meet um, on Tuesday, and I'll do some review examples. That way, working with the old test and just kind of covering some examples from the practice test. And then, of course, again, at this point, study the new material and then go back and refresh yourself with the quizzes and the tests of examples and ideas that may be a little bit rusty. For some of you, nothing may be rusty. You put in plenty of time and you don't really have to worry. Just knock out the new stuff and you'll be ready to go. So like I've told my other classes, for the classes that meet online on the schedule, I will have a meeting at the early part of the week where we can do some review examples and do additional problems from the new material. And so again, be wise about the choice of study time. Break things down. If you have other obligations that you need to work in, get the busy work done first, and then focus all of your time on the mathematics, as I'm sure it will be more difficult. And so if I don't see you at the office hours, I certainly will be getting in touch via email and messages on Blackboard. And we'll see you next week as we meet for our final time, and then you'll take your final exam. So enjoy the cool. I'm enjoying that, and keep yourself safe, keep yourself healthy. And just remember the relaxation time is on the way. I know those of you in the early college, high school still have high school, but I think by the time the holiday season comes, it's just time to enjoy being with everybody. I've noticed when I used to have my office near the early college, high school at San Jack, by the time the holidays came, everybody was just having a party at every class. So I guess that must be nice. Professor Ron didn't have that when he was going through school. So I like the new I like the new changes. It's good to have a festive atmosphere. But I appreciate your attendance today. And if I don't see you at office hours, I'll see you next week. Bye, everybody.
Have a good day, sir.
Thanks. Bye, everyone.